three warm-up problems. Limits and definition derivative, which is like in this Stewart textbook, it's chapter 2. It's all chapter 2. Limits are 2.2, like number 2. Limits to infinity are 2.3. Number 3 problem is like 2.5 and 6. That said, that gives you places you can go for suggested problems. On the top one, there's two ways to do it. I'm going to talk about it, because if you forget the rule, it doesn't help me to tell you there's a rule. When I think of a very large number, like going to infinity, when I think of a million squared on top over 3 times a million squared plus 2. When I think of a million, I don't really have to think about the 2. Do you guys agree? And when you see that, then what happens is the rule is just look at the coefficients and make sure they go out, and the answer to this is 1/3. Yeah, guys, the answer is 1/3. When in doubt, could you use your calculator, plug in some big numbers, and see what it approaches? Sure, you can do that. Now we have to be clear, the second I have a limit that looks like this, x squared over x cubed plus 1, 3x cubed plus 1, whoops. Guys, you put the million in and think about it, well now it's x squared over x cubed. Well now it's 1 over x, which that goes to 0. Remember when there's an x, Albany hung up on me. Alright, we'll keep rolling, hopefully they'll connect again. Alright, so again, we have that condition there. Alright? Oh, I heard him. There's the dark again. Oh, God. Alright. And lastly, guys, if I do it the other way, x goes to infinity of x cubed over 3x squared plus 1. Guys, there you see that. Yeah, on the black one I changed them. The black one's a different example. So this was the one we did, but I'm talking about the other. This is a new problem here. Alright, this is a new problem. And the point to this problem is that when the denominator has a higher order term, it goes to 0. And when the numerator has a higher order term, in this case it's positive. You guys agree? Positive over positive, so it goes to positive infinity. Again, those are your three choices often. It either goes to a value, it goes to 0, or it just gets big, right? It goes to infinity, positive or negative. Those are the cases of infinity. On number 2, before you do anything, you stick 3 in the denominator, and guess what? Unfortunately today, it is 0. Yesterday, Albany, when you were gone, I had a big ugly one. You stuck in the value, and the bottom wasn't 0. So you should have solved it in 20 seconds. Because the bottom is 0, I am forced to factor. I think x squared comes out. On the top, I think it's x minus 3 quantity squared. Boom, boom. I think I get the answer is 0 over 9, which is still 0. This approaches, the limit of this one is 0. Again, algebraic. It was already expanded, so the next thing was to factor it. If that didn't work, we could think about the conjugate. That wouldn't work. Then we go to graph. And if that shows it's not a limit, then it doesn't exist. Number 3 says use the definition of derivative, which I shouldn't have to tell you guys. This you should know. When I say derivative, you should know it's f prime, and you should know that it's this limit. That said, I said show that f of x equals x squared minus 3x plus 7 is f prime of a. So, if I'm going to show this, I have to go out the steps. So I have to put in a plus h squared minus 3 times a plus h plus 7. That is f of a plus h minus, this is the green part, I just did this, minus, I'll do this in red, I'll put in a squared minus 3a plus 7, all over h. And then I have to grind this sucker out. Limit as h goes to 0. A binomial squared, guys, is a trinomial. If you haven't memorized this yet, you might want to. And if I distribute the negative, and again, some students, Tony, tend to just write a bunch of stuff. By actually go through to make sure you have this, and then I am looking that you actually have the signs to cancel it all. And if you lose something, like you know the answer is -3, search out the H here. Because the next thing I'm going to look for, hey Sam, answer that, would you? So I get 2a plus h when I -3 over h. The h's cancel, goes to 0, and I just proved that f prime of a is equal to 2a minus 3. All right? So, all right. So that's that one. I'm going to put a dual page if you're copying this down. I got a phone call because I'm a popular guy. I doubt you guys can do 4. Well, I don't know. You should be able to do 4, and you should be able to do 5. We'll see if you can do those. Oh, I'm still recording. Now I'm going to pause this. So everybody, number 4 says estimate f prime of 10, and I should have said that f of x has the following data table, right? Has the following table. Okay, and I just abbreviated following. So f of x has the following table. In minutes is the time on top, and degrees Fahrenheit is in the bottom. So maybe I threw a big hunk of meatloaf in my oven. All right, and maybe I turned the oven to only 200 degrees. All right, and over 15 minutes it goes up from 80 to 102. And I said, hey, what is the tangent line at 10? Well, you can't do the power rule. You can't do f of a plus h minus f of a over a plus h minus a as a limit of h. You can't do any of that because it's a table. What you can do, though, is we can find the secant, right? The secant line here, which I'll do as 97 minus 88 over 10 minus 5, which is 9/5 of a degree Fahrenheit per minute. And I can do the secant line on the other side, which is 102 minus 97 over 15 minus 10, which is 5 over 5, right? Which is 1 degree Fahrenheit per minute. And the best I can do to estimate f prime, the tangent in this case, would be to take the average of the two secants. So guys, I would take 9/5 plus 1 over 2. 1.8 plus 1 over 2 is 2.8 over 2. How about 1.4 degrees Fahrenheit per minute? And that's our best estimate of f prime. There is one other way. Yeah, this will be on the test. This could definitely happen. Yeah, and this, if you guys are curious, this is in Chapter 1 review. Some of the suggested problems. Oh, now we got light again. Welcome back, Albany. You see a TV, but everybody, on number 4, you could also graph it. Oh my God, I want to throw up thinking about it, okay? But I could sit here and make a super good graph. 0 is 80. 5 is 88. By the way, this is not a super good graph. This is a really, really super crappy graph. And then at 10, you could draw the tangent line and find it's 1.4. All right? It would take a ton of work to graph it and do that. That is not the way I want to do it. I want us to understand that we can estimate by using secant lines on either side of the value we're looking for. That was on the quiz too, right, with the emptying of the tank. That's lesson 2.1 too. Number 5 is a little tough. Draw f of x where f of x is increasing 0 to 4 and decreasing 4 to 8. Okay, that is not hard. Guys, that is not hard. I hope everybody has at least this. 1, 2, 3, 4, 5, 6, 7, 8. And maybe I just draw it this way. Maybe you have this, right? That's fine. Yep. Okay, and Megan just said, I want to make it a V because I want an undifferentiable point at 4. Fine, right? Mine was differentiable, yours isn't. We're both continuous. But here, do you guys catch what I said? I want f of x greater than 0 from 0 to 6. And from 6 to 8, I want f of x to be less than. So I'm going to change the graph here for that condition. I am doing the second condition now. Everybody, whoops. I want you to see the difference here. Do you guys see why this is increasing? Right? That is this. Do you guys see when you look at the graph, y 4 to 8 is decreasing. That is that. But the bonus part was this. I wanted it positive 0 to 6. That's the part f of x is above the x-axis, 0 to 6. You guys agree? It has nothing to do with increasing, decreasing. And then I said, hey, from 6 to 8, I want it to be less than 0. All right, that should make sense to us. The bonus is hard to mix in, though. I don't expect you to be able to graph this. I expect you to be able to read the graph. So if I put up a graph, you guys, I'm going to go double page. If I put up a graph like this and give you some instructions, and then we're going to do an IVT. I can make a graph here. Let's make this -5 where it starts. -4, -3, -2, -1, 0, 1, 2, 3. All right, we'll go up, and then we'll go down. We should be able to tell me where the graph is increasing, decreasing, where f of x is greater than 0, and where f of x is less than 0. And I mean, literally, I'll pause the video for only like 20 seconds, because you're either going to know where those regions are right now, or you're not. All right, so increasing, there is only one little short spot here, guys, and I think that's -2 to 0. Decreasing, there is one long spot from 0 to 3. It is not increasing or decreasing where it's horizontal, but it is positive. I'll do it and go above the x-axis all the way to here, right? So I think that is -5 to 2. And finally, it's below the x-axis right there, 2 to 3. Everybody, that's the difference between increasing, decreasing, and the resulting values. It is very important, and I put this in the document. It's very important we understand the difference between f of 1 and f of x equals 1. Everybody, I don't know, I'll put a scale here. Okay, 5. On my graph over here, f of 1 is 2. All right? On my graph over here, where f of x equals 1, I don't know. God, I hate when I have bad graphs. Is like 1.5. Right? It's the understanding that this is, look at x, find the y value. This is y, find the x value. All right? Every year on the first test, I have students who invariably screw that up. All right? And again, if you do a little studying ahead of time, you're okay. I feel a little bad, Albany. I hope you got my email. It's a good chance for me to talk about this real fast before